Hello and welcome to this lesson on artificial intelligence in sciences. Picture a future where drones navigate challenging environments with the precision and coordination of a natural swarm. As we explore predictive control technologies, we are on the brink of achieving seamless autonomous drone operations. By learning from nature and advancing our capabilities, we are setting the stage for a new era of efficient, synchronized drone swarms that can tackle complex tasks with confidence and reliability. This unit provides an overview of the application of AI for mathematics. Let's get started. Natural swarms, like those of starlings and bees, exhibit perfect synchronization, which is challenging to replicate in drone swarms. Drone swarms offer significant advantages, including large area coverage, data collection, and performing tasks like transportation and construction. Current drone swarms are centrally controlled, unlike natural swarms that operate without a central leader. Biological swarms follow three key behavioral rules: cohesion, or staying together, repulsion, or avoiding collisions, and alignment, or coordinated movement. These behaviors can be mathematically modeled using potential fields, or PFs, to regulate distances, adjust speeds, and ensure obstacle avoidance in drone swarms. With PFs, drones are attracted to their goal, like a magnet pulling them in the right direction, which helps them move toward where they need to go, while at the same time being repelled by obstacles, like being pushed away by an invisible force, to avoid collisions. Shield agents, or virtual repulsive forces, are used in PF models to prevent collisions by guiding drones away from convex obstacles. In scenarios like dense forests, shield agents help drones navigate by repelling them from trees and branches, ensuring safe passage. While effective, shield agents can slow down swarms, particularly in environments with many obstacles. Reducing repulsion forces to speed up swarms increases collision risks, requiring a balance between safety and efficiency. Predictive control mechanisms in aerial swarms enable faster, safer navigation in complex environments by anticipating obstacles and adjusting behavior accordingly. Unlike purely reactive PF models, predictive control allows swarms to adapt to varying obstacle densities and maintain coordinated movement. Inspired by biological swarms, the Nonlinear Model Predictive Control, or NMPC, equips drones with predictive capabilities, enhancing synchronization and collective behavior. NMPC combines elements of separation, propulsion, direction, and minimal acceleration to optimize flight paths and improve energy efficiency. Experimental results showed that NMPC-controlled swarms outperform PF models in cluttered environments, achieving faster, more synchronized and collision-free flights. To conclude, traditional potential field models explain swarm coordination through local interactions, but struggle in complex environments, compromising speed and safety. The NMPC approach offers significant advantages for navigating crowded areas like forests and urban environments, enhancing swarm coordination and safety. Predictive methods like NMPC can improve swarm autonomy and reliability, which is essential for building public trust in swarm technology.